Welcome everyone back to Fun with WebGL 2.0. This lesson is going to be slightly different because it's going to be two parts. There's a lot to cover, quite a bit of theory and quite a bit of code. So the first part is going to be a lot of theory, and then I will make a second video which I will really just step through all the source code to accomplish what we're trying to accomplish. Today's topic of discussion is shaders. This is going to be the bread and butter of your rendering engine. They are part of what is known as a programmable graphics pipeline, where you, the programmer, gets to write some of the code that takes the data and converts it into pixels on the screen. In all honesty, all the heavy lifting is done for us. The only thing we need to worry about is the Vertex and fragment shaders. And these shaders, all they really are is just these little programs that we get to write that we upload and compile on the GPU. And we get to write these programs in a language called GLSL, which is a C-like language created for OpenGL. And here's an example of that on the screen. Right here I'm going to show you the old version and the new version in case you're coming from WebGL 1.0. And we're going to start with the Vertex shader. And the Vertex shader is a function, or I should say a program that executes on every vertex in a vertex array. This is where we actually start doing all our transformations. So like we did in a previous lesson, we start off at origin and we start rotating and moving things around. And this is where we actually start calculating. This is when we start moving all the vertices, all the triangles and everything all over the place. So where, your little ball can exist, 50 feet away from the camera. This is where you actually do it, because this is the quickest and easiest way to actually modify hundreds, if not thousands of vertices. If you actually had to do it on a CPU, it would be really, really slow. So where GPU does it so much faster. So this is the reason why we upload all our data to the GPU, because the memory is much faster, and we have all this code to execute it, because that's really the whole point, is for performance and optimization. It does a really good job of transforming and doing all these mathematics. So this is really, that's the whole point of the Vertex shader, is really just to do all this crazy math to move vertices around. And it does other things too. Helps you calculate lighting, normals, and a bunch of other things. You can do a lot of things, but primarily, this is where all transformations happen. This is where you're going to do your scaling, your rotation, and your translations. And translations is really a fancy word for move. This is where you actually move things from one position to another position in the 3D world. It's through the translation type of transformation. Like, the one thing that I was surprised to learn when I started doing WebGL is that all 3D models exist on Origin. They all do. If you can imagine it in your mind, like all the things in a video game, they're all compressed into one tiny spot in the 3D world. And it's the Vertex shader's job to actually move it, to actually expand it, like kind of like the creation of the universe, where it all starts in one tiny little spot and it just explodes, the Big Bang, and everything gets spread out. That's how you can picture the Vertex shader doing. It's like everything exists right here in the center, and boom, everything just gets thrown all over the place. So Vertex shader is technically our Big Bang theory right here. So enough with this crazy talk. Let's talk about the code that's on the screen. The first thing we're going to start with line 2. And you'll notice that in WebGL 2.0, we kind of have to tell what version it is. And we're using version 3 of ES. WebGL is technically OpenGL ES version 3, which is the mobile version of OpenGL. So it's pretty much OpenGL that you would normally get on desktops, but it's a smaller, more portable version. And WebGL is kind of even a little bit smaller and portable than ES, but it's pretty much technically should be the exact same thing. So in version 2, we have to declare it. We have to declare it for both our fragment and our Vertex shaders. WebGL 1.0, you don't have to declare what version, because it is version 1 is version 1. Because it's kind of weird, because WebGL 2.0 is using OpenGL ES version 3. So that's pretty much part of why you have to give all these weird versioning numbers. The next thing up is attributes. Attributes are where we actually do all our array uploading. This is where it handles all our vertex arrays and other things like normals and UVs and everything else. You notice that in the two different versions there are different names, but they're the same thing. They're both attributes. But in 1.0, it would actually say attribute. And in 2.0, we actually say in. It's like an input. And all it is just the arrays. There are the buffers that have been created in the last two lessons. They actually have a name. They're called VBOs. They are vector buffer objects. They're really kind of like the starting point for our vector. That's why it's a vector shader, and the A position is really where all our vector array comes from. So all attributes are just VBOs, vector buffer objects. Then if we start doing line 5, we have uniforms. Uniforms are the same way, no matter which version you're talking about. And uniforms are your global variables. They're the global variables that you get to set per frame or every other frame, or whenever you need to change a certain value in a shader. Where buffers, they're not supposed to change. They're supposed to be kind of static. Most of the time, they will be static, unless you're dealing with certain things that requires you to actually change the array, which might have to do some kind of procedurally generated meshes or things like some advanced stuff like that, is when you kind of need to be more dynamic. And there's other like extra dynamic stuff. I forgot what the extra keyword is, but it's for UI, where it's kind of like it's the data is going to change at every frame, where a dynamic setting, it's going to change per every other frame. And then we have static, which means it's not going to change at all. So let's stop talking about VBOs, and now let's move on to line 7. In line 7, you'll see there's another change. These are called varying variables. Varying variables are the variables you set up in your vertex that will get passed to your fragment. And any value you set into it gets interpolated between each vertex. So if you have a one vertex, you set up a variable and you set it to 1, and you have the second vertex and you set it to 10, when it goes through the fragment shader, it would actually change that varying variable to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It would actually go through all the steps needed to get from point A to point B. So that's what varying does. And but varying, it changes in WebGL 2.0. It now becomes an output variable. But it's still called a varying variable, but it's an output. And when you create an output variable, then you have to create an identical variable, but it's an input for the fragment shader. Well, you'll see that later. So those are pretty much our main variables that we're going to have at the beginning. It's going to be our attributes, our uniforms, and then our varying. Now we get into the program. The program is where main void.start, and this is very C. This is, if you're a C programmer or usually in any programming, you'll see it in Java or C# and things. You'll always see kind of a main function somewhere in there. So that's the entry point of where the application actually starts. And inside the function, you'll see some of the things from our previous lesson. One of the things you have to set in every vertex shader in your main is GL position. That is kind of like a global variable that, it's kind of like the final output or the main output of the vertex shader. It's GL position. We need to set it. And, most often, depending on what type are you doing, if you're doing 2D, then you don't need to really do too much mathematics. But when you're doing 3D, you didn't have to start doing matrix transformation. So that gets a little bit more complicated than what we have now. This is really just something simple. We're just, rotating something and then moving it at a certain radius. And in case you didn't realize it, all the vector variables can be accessed by its components or at its whole. As you can see, we can access a position, .x, .y, .z, .w, or there's the vectors can actually also be accessed by a different component set, which would be R, G, B, and A. Either one doesn't matter. You can do X, Y, Z, W with colors and vice versa. You can use R, G, B, and A with position. It's interchangeable. It does not matter really. Vector 3 or vector 4 is the same no matter what. It's just you can kind of use the components to access the specific part of that array. So that really isn't much I can say about the Vertex shader at this point. Like I said, the most important thing is GL_position. There are other global variables you can set. Like in this one, we're setting GL_point size. There's a few others. I just don't remember them. But if you look them up, they have different purposes. Now we're going to move on to fragment shaders. Now, fragment shaders, in all instances, is where all the pixels are colored. Between the vertex and the fragment shader, it has other steps in the pipeline that kind of forms all the position, like a rasterizes all the positions and all the pixels that it needs to draw. And then it takes all these pixels and asks the fragment shader, what do you want to color this pixel? We know there's a pixel supposed to be here, but how do you want to color it? And that's really the whole point of the fragment shader, is to choose a color for the pixel that is automatically generated between groups of vertex. That's all it does. You can do some really crazy things. Here you might actually start doing lighting in fragments, blending colors. You do textures in the fragment shaders. That's really where the meat and potatoes of fragment shaders are. It's really just picking a color, and it's basically setting a color, or like I said, like you're dealing with lighting, merging things together, textures. This is where it all happens. And in WebGL 1.0, you had a global variable that you can set, which would be GL frag color. In 2.0, that got removed. Now you have to set an output variable, and the reason is that if I remember reading correctly, by OpenGL 3 or 3.1 or whatever, you can actually return more than one set of colors. I'm not sure how you do that in WebGL, or if it's even supported in WebGL or in OpenGL ES. But that thing was removed in general from OpenGL. So if you have to set a color. So you just write one output variable. You can name it whatever you want. And in my case, I just call it final color. And all you do is just set it with a vector 4, because a color in the shaders are for components. There's R, G, B, and A in alpha. Alpha only works when you have a certain setting turned on. So if you were to change the alpha, you'll notice that it does not get transparent at all. I think it's called blending mode has to be turned on in WebGL to actually have alpha to be effective. What else? Yes. We also have the in vect3 size, which is on line 24, our varying variables. So like I said before, in our vector shader, we have size set as an output variable. And in our fragment shader, it's set as an input variable. So this is where it comes in, and you can use it to do whatever you want. And in this case, I'm actually not using it in the fragment shader. And one thing you should kind of realize, which I learned by trial and error by accident, which kind of screwed me up a couple of times. If you create a variable in any of your shaders, but you do not use it in your main function, they will be optimized out during compiling. So if you create a couple of uniforms or attributes in your shaders, and you're not using them at all in main, they will not be accessible in your link program, because they will be removed. Because if they're not being used, there's no point of having them. So you have to. So in case that happens, like why isn't this working, or why am I getting a -1 for a specific location when I'm trying to get a location of an attribute or a uniform? That's probably why, because it's not being used in your main program. So just keep that in mind when you're creating variables. If they're not being used, they will actually be completely removed from the compiled application. Another thing to denote in fragment shaders is that we're telling it what type of precision a float is. It's because it's not set by default in WebGL. The Vertex shader does have it set by default. There's a default value, which is high P, which is the highest precision you can set for a float. There's high, low, and medium. When you use high, you use more processing power, and it just uses up more time to do the math. And medium, it takes less time, and low is less. Each one has kind of a purpose or a usefulness. For some reason, they could not decide what default to automatically set fragments. Since there's no default, you have to set it yourself manually. You can set a high if you want in Vertex shader, but you technically don't need to because it's already the default precision. And in case you're not sure what precision is, it's really how far down the decimal point the float goes. I don't remember how far each one goes, but let me guess. Let's say high can go down to 20 decimal points, medium can go down to like 10, and low goes down to 5. So the less decimal points, the quicker any of the math gets done. There's like a kind of rules and thumbs I've read that high P is very good for position, because there's so much all over the place, and you're stuck between -1 and 1. So you want as many possible numbers as possible as you can get. So high precision is used for positions. Medium is good for. I wrote this in my notes. Sorry. Medium is great for textures because a texture is smaller. It's not like a huge web universe. A texture can anywhere be 256, 512. I forget what after 512 is, but it has to be divisible by 2. So your textures should be divisible by 2. You can have textures that are not, but it's generally better to have divisible by 2 textures using your shaders because it will execute faster. Just the math, the way everything works, is just divisible by 2 is a lot quicker. So medium precision is good enough for textures, and when you're dealing with colors, low is perfectly fine if you want to use up less memory for colors. So technically, I'm using medium floats for our final color, which I can probably set it to low precision, but I don't need to get that much extra tiny fraction of a millisecond of performance in this shader. I guess if you really want for the best possible, you can probably set it, but you don't need to. Most often, you're just perfectly fine. Just set it as the fragment shader by default at medium, and you're good to go for all your shader needs. That's pretty much everything I can really say about shaders. So the next thing we're going to talk about is VAO, vector array objects. They don't really exist in WebGL 1.0. You can use them by enabling extensions, but in WebGL 2.0, they're part of the context. You have full access to it. You don't have to go through extra steps and hurdles to get access to VAOs. Trying to see how to explain VAOs. VAOs are a way to save a state of attributes. Like I said before, attributes in shaders and uniforms, they have a location position, and they're basically based on where they exist in the order of the application. And when you're doing your code in your render loop, you have to find a location, enable the location, and then set a pointer to the buffer you want the attribute to kind of point to. When you're dealing with multiple shaders, that means every time you turn on a shader, you have to reset all that stuff, and then you turn it off, then you move on to the next shader, you turn the new shader off, and you got to reset everything. That can take up a lot of time and just really complicates your code. So I think it was a OpenGL 3.0. Or maybe 2.0, I can't remember, but I definitely in WebGL 2.0 you finally have full-on access natively, and VAO basically allows you to pre-set up all your attributes and all your buffers as like some type of state or a structure that you can then set just that alone for your shader. So ideally, you do all that setup in your initialization. You do all the binding and whatnot to your VAO, and so you can then set only that during the shaders. And on screen, I kind of have some things to help you kind of visualize how it all looks and how it works. So you can imagine VAO as like a variable or a struct, and within the struct, you'll have one thing called element array buffer, which is just your index buffer. I'll explain that in a minute. And then you have your attributes, and these attributes are basically just the array attributes that will exist in your shader. So normally you're going to probably use more than 3 buffers, attribute buffers per shader. There might be more, but 3 are going to be probably most of the time going to be your max. And each device kind of has a limit, but I don't know what the limit is by default. But like everything's going to be different. Like your desktop, your mobile phone, your web browser, they're all going to have different maximum attributes. There's some code somewhere you can actually call and find out how many attributes you can handle, but it's really not that big a deal because, like I said, you're most often just going to deal with these 3, especially with WebGL. You're going to have your position buffer, which is our main buffer. This is where all the Vertex exist, and this is where our Vertex shader is really just going to iterate through. And then you got your normal buffer, which normals are just the directions, like what direction is the vertex pointing. The normal values are very useful for lighting. If you're not dealing with lighting, you don't need normals. And then you have UV. UV is the position in your texture that the vector kind of points to. So if you're using texture images, you need UV values for each vertex. And then back to index buffer. So you kind of have your position, your normal, and UVs, and your index buffer is what ties them all together. So when you're looping through and you have an index set up, it would actually start looping through your index buffer, and the index buffer will kind of, let's say, in unison or synchronizes the looping through all the other buffers that you have set in attributes. So if you're on the first vertice, it'll get the first vertice in position for your shader. Then it'll pass the first normal for your shader and the first UV for your shader. So it kind of just syncs all that up for your Vertex shader code. So that's what index is all about. It's just really just to kind of synchronize everything. And index also serves another purpose. When you're dealing with generating meshes, if you don't have an index, you will most likely end up duplicating vertex, especially when you're dealing with normals. There's always been this thing that when you watch about WebGL or OpenGL, is this question: how many vertices you think does it take to make a cube? And most people would just say there's only 8 points in a cube. Yes, and that's true. There's 8 points in a cube. But when you're dealing with WebGL, and when you actually start doing this and start building things in, from raw numeric values in arrays, you start to understand why these people say you're wrong when you say 8. It's really 32, because you got to duplicate the vertice, because each vertex can only have one corresponding normal and UV. So if you, for some reason, you have one position that has 2 separate normals, then that position has to kind of exist twice. Same thing with UVs. If there's a position that has 2 separate UV values, that position has to exist twice in your array. An index can sometimes, depending on how you use it, can allow you to not duplicate vertices. So in an instance of making a cube, you can have your 8 points, but then you can have your index set up to actually use those 8 points and kind of generate 32 points. That's if you're not using normals or UVs. Like if you're just going to straight up make a cube and just draw lines, then you can actually get away with using as little vertices as possible and have index kind of handle all that work for you. So instead of having 32 vertices, which is 32 times 3 floats, it becomes a big kind of an array. You only need 8 vertices times 3, and index is an integer. So integers use up less memory than floats, so you end up using less memory in general by going that route. But like I said, it all depends on the data and what you're trying to accomplish. Like if you need lighting, if you need textures, then you're most often going to start duplicating your vertices. And it becomes more apparent when you start creating things from scratch, or when you start loading in object files down the line. So let me finish this up. So that's pretty much what a VAO is. It's just a state you can kind of save for your shaders. And the graphic I kind of set up on screen is that, once you have all this set up, every time you want to turn on a shader, all you have to do is just set the attribute state to the VAO that you want to use. All this stuff is kind of pseudocode down on this page. None of this is actual real. It's just pseudocode that kind of illustrate what I'm talking about. And like I said, I'm illustrating that if you can either do that one line of code, or if you're not using VAOs, like in WebGL 1.0, then you have to do the second step where the location, activating, and the pointing, and then you have to do that for every single attribute. And like in this case, I have to do this 9 times. This is not counting index, because index thinks this. I forget the code for indexing, but I think there's an extra 2 steps, so it's like 9. It's 11 steps basically to set up your buffer. A buffer that not your buffer. I'm sorry. It's 11 steps to set up your shader with all the buffers that you're using, and doing that on the render loop, it's kind of sucks. That's 9 bits of code you're running. That's 9 calls to the GPU you're dealing with. It'd be nice if you can just do a single call to the GPU and just continue on and just execute. And that's what VAOs does. It just gives you that ability to kind of just speed up the process and take away a lot of that garbage that doesn't need to be repeated so much. So that is really the whole purpose of VAO, and we're going to start using that in the code. We're going to stop setting up all these things in the render class or in the render loop callback. So yeah, that's pretty much it. Really, all I would have wanted to say about shaders. Man, I started this at midnight, and it's almost 1:30 in the morning. I can't believe it took me almost 90 minutes to record 30 minutes worth of audio. This was long. This is like the longest recording I've done so far for the series. I like to try to keep things under 10 minutes, but this is a big topic because shaders are probably one of the most important things in your arsenal when it comes to OpenGL. Without it, there's nothing on the screen, because shaders is what allows you to take all that information and just compile it into an image. And you do this like 30 times per second. So it's very important. Like everything in your shader should be as optimized as possible, because the more optimized, the least that you need to do, just makes it faster and helps you render things a little bit quicker. I think the only thing I can probably say is that down the line, shaders should be kind of dynamic in a sense. Like you might have like a shader creator which has pieces already predefined, like emissions, default colors and lighting and everything else. And ideally, you kind of say, I need this piece, this piece, this piece, and that piece. And it kind of just quickly takes the bits of code and kind of makes a shader program for you. When you start dealing things like that, you kind of have to predefine the location of a lot of your attributes. And we're going to do that in the code. We're going to predefine all our buffers. So this way, no matter what, position will always be 0, normal will always be 1, and UV will always be 2. So no matter what. So in like for one, if you make a shader that has a position and a UV only, position will be 0 and UV will always be 2. If you did not predefine it, UV would actually be 1 because it would be the second attribute in the shader. So predefining it will actually help down the line to kind of standardize things for your shader and your framework. So yeah, that's pretty much it, really. Shaders are a very complicated subject, and I'm really interested in them, and I really want to get really deep into it. And the more math you know, the easier shader creations will do. But there's so much shader code out there that just about any effect that you're looking for, you probably can't find a shader already out there in the source code. And some of them probably explained, and some of them probably not so explained and how it all works. But yeah. All right, so I'm about to get very close to. All right, I'm already over 30 minutes. So let me just end this here. And this is the end of me talking way too much for way too long. And I'll see you guys in the next lesson where we actually get to write some code and really get things working. So see you at part 2 of lesson 3.